So what is the equation? Q is Cm delta T. So this formula is about what? It is about heat, not about specific heat. It is heat here. About heat needed to change the temperature of an object by delta T. What is specific heat? That constant in the equation, and if you have to define it, you need to solve the equation in relation to that quantity. So that specific heat is specific. That's why the term specific is used. It is a constant specific for the substance of interest, and it shows how much heat is needed to change 1 unit mass of a substance by 1 degrees Celsius or by 1 calories, depending on the way the temperature is measured. So why I have defined specific heat in this way? Since if mass is 1 kilogram and if temperature, suppose in degrees Celsius, which is more popular in this case, has changed by 1 degree Celsius, then C would be exactly equal to the heat being added. That's why specific heat is the heat needed to change the 1 kilogram mass of a substance, the temperature of 1 kilogram mass of a substance by 1 degree Celsius. And the unit of measure of that specific heat is, so heat is measured in joules, but the popular unit is calorie per, instead of base SI unit kilogram, gram is preferable here, and temperature in degrees Celsius. So the more popular unit of measure for the specific heat is calorie per gram per degree Celsius. In the slide, another unit is introduced, the so-called dietary calorie, and what is it? It is 10 power 3 calories, or 1000 calories is called dietary calorie. And let me continue with the next slide regarding heat of combustion. So, what is this heat of combustion? This is the heat released during burning. But why is it important? Because within the human body, food is oxidized. Burning is also such an oxidative process. There is an analogy. And what else? The main idea. If food is burned outside the body, the energy that would be released will be equivalent to the energy released within the body as a result of oxidation process. Is it correct? This was proven. In what way? Via measuring heat of combustion. How to measure it? Using the device that is called calorimeter. So there is, in the slide, picture of a calorimeter. So we've got different types of calorimeters. This is the so-called oxygen bomb calorimeter, because the food is burned in pure oxygen atmosphere. And what is the structure? There is a chamber in which food is placed. Also, there is so that that chamber is surrounded by water, and there is a way of measuring the temperature water. So that if those here walls are completely isolated, which means that any change in energy can occur within the body of the device. During burning of the food, heat would be released. It will be absorbed by water. Water will change its temperature. And according to the law of conservation of energy, heat released is equal to heat absorbed by water, which means that can we calculate the heat absorbed by water? Yes, using what equation? The one which we have just written to define specific heat, this equation. What is C in this case, specific heat of water? What is saying? The mass of water being exactly there within the calorie unit. What is delta T? The change in temperature as a result of that food burning. And we can measure what? The heat being absorbed. But it is exactly equal to the heat being released, which is called heat of combustion. So in this way, heat of combustion can be measured. Why? To know what is the energy content of food. And let us proceed, since there is another picture, which same absolutely analysis can be applied to show the validity of the first law of thermodynamics for living systems. There is a body being placed in very tight chamber, not moving, since it mustn't perform any muscular activity. And you see, this is exactly calorimeter. There is water here. Temperature can be measured. And what can be done here? To measure heat released by the burning. And if the food being fed is burned in a calorimeter, the heat of combustion can be preliminarily known. And if the heat of combustion is equal to the heat released by the burning, this means that we can prove the validity of the first law of thermodynamics. So by and by, if you have read below, this picture is published, you see, so many years ago in a French scientific journal. So long ago, this validity was proven. So let us just say important things regarding what that method applied to prove the validity of the first law. There are some deviations, some small corrections needed to be performed. See, some molecules are burned within calorimeter, but are not oxidized within the body. What is given here? Cellulose example. Also, some residues of proteins also cannot be oxidized and are excreted in the urine. So thus corrections are needed for complete validation of the law. And in that section, mechanical equivalent of heat. So in this section, a conversion factor is introduced. I told you that especially in food chemistry and in calculations of energy content, the food calorie is the preferable unit of measure. So we need to, solving different problems, to be able to change calorie into the joules and vice versa. And the correction of that transformation or conversion factor was given, was suggested, was introduced by James Joule, who performed an experiment. So specific pedal system was used to stir water, and as a result of friction, the temperature of water is increased. So in this case, we've got mechanical work being transformed into heat. In this way, he was able to derive the exact value of this transformation factor. And also, there is a discussion here regarding the rate of heat production. So if you need to write mathematically, what is this rate of heat production? So if there is rate, the term rate means change over time. So thus, heat being changed per unit time, this is called the rate of heat transfer, heat production. In case of the James Joule experiment, it is heat production as a result of stirring water, and the unit of measure is discussed there, which is joule per second. Also calorie per second is applicable, and in biophysics specifically, instead of those terms and symbols delta, we will substitute the symbol by symbol D. So if delta means change in, D means very small change, which in the mathematics language is called differential. So, and instead of writing delta Q over delta T, we will write dq dt, the very small change in heat per unit time. And using that way, let us once again revise Fick's law, which we can write in this way. Flux being the amount of, very small amount of mass being transferred per unit time, per unit area. That's why I'm introducing here symbol dA, which is proportional to the concentration gradient. See the way we write gradient now. It's very small change in concentration per unit length. Also, we know what Fourier's law which is what? The flux of heat being the heat being transferred per unit time, per unit area, which is minus K temperature gradient. Also, let me write what Poiseuille's law in this way. It is about volume flow rate. What is volume flow rate? The change in volume per unit time. And it is extensively written by R power 4 over H eta, and then so we may write dP over L, but let L being the length. But in case of unit distance, you may write dP dx, which so also this can be written as dP dx, which is what? Hydrostatic pressure gradient or mechanical pressure gradient. So gradient of pressure producing flow. And what else? Since this is the lecture, today's one, easy, maybe one of the easiest according to me, very subjective of course. So next time, topic is about the physiological applications of heat transfer. So, for being able to discuss that, those applications within human body, you need to know the theory. And as usual today, 3 groups will sit for test. Absolutely certain you must be that each time some students will have tests, and also they have to submit their lecture notebooks, rough notebooks, to check them by me. So that's group 10, 11, and 14.